Come again? Yeah. So I'll come to that. So let me, I think this will solve your conundrum. Okay. Hold on. Right. So let me understand if this is what you were trying to say. So one question had something like this. So the f of b was this Vn was something like this, right? And I'd asked you to, I think I had set the question point of Vn such that it's on the flex, right? Yeah. So essentially the short form is I messed up. It was not intended to be, but let's assume that you have it here. So by the way, if you are wondering, I mean, I won't penalize you for my fault. So we'll take care of it. So, so let's assume you have built a nonlinearity which is like this, and you are sitting here. In fact, there was one question in after one of the classes. I think you had asked me. Right? You had asked me that. So what happens if you are sitting here? So clearly, you see that. I mean, the entire genesis of whatever we have been doing is based on the fact that the differentials exist, right? So clearly the differentials do not exist here. So you'll not be able to solve using the methods that you have. I mean, I have been pushing throughout this course. Now, another question, another approach to this might be that, hey, I mean, I will not use Taylor series. I will assume that let's assume that this line goes on. I'll assume that this straight line is the solution to the problem, and I will evaluate. I'll find out the solution to this network, and then I will do the same thing, assuming the other line is ubiquitous, and I'll find the solution to the network, and then I'll get a set of values for which the condition are valid or invalid, right? Where Vn, I mean, where if I solve for Va, I will get a set of values for which maybe I'll get this is valid, in other set of values where this is valid, then I'll find out the intersection points of subset, and then that's my solution. In principle, you can do that, but it may turn out that the solution might not even exist. And that shouldn't surprise us, because we are essentially trying to find out the roots of some nonlinear equation. Right, so you are marrying the current. You are marrying the current through this and this. You are equating those two currents, and you are essentially trying to find out the roots of some nonlinear equation. And it's not necessary that you should have real roots, or even you should have any solutions at all. Right. So just because I have come up with some arbitrary thin curves doesn't mean that in reality you can find devices which give you that. Yes. So forget about incremental. Not even, I mean, incremental definitely will not be able to do, right? Because your derivative doesn't exist. In other one, correct.
So that's why you wouldn't have been able to.
Correct. So it's not because of that per se. It's basically because the differential doesn't exist. The Taylor series, you cannot even bring it around that point. That's essentially the moot point. So now, but what I mean, this is actually a good segue. So let's assume that it's not that sharp, right? So you can have let's assume you have some device which has an IVD characteristics, which is maybe like this. Continuous, all differentials exist. This is in principle possible, right? I have not done anything weird. So in this case, you can do you can actually do a full-blown analysis and figure out. I mean, let's assume this is an inverted parabola. So you know this is of this form of which one, y square equal to minus x form, right? Shifted up and down. So you write out the equation sorry, y equal to x square. Y equal to y square form. Yeah. So you can write it. I mean, you can shift the entire thing up and down and basically do the full-blown analysis to figure out what will be I and Vn, including when Va has a sinusoidal input on top of quiescent. So now let's say that I will not do this full-blown analysis. I will do whatever we have been doing throughout the class. That is, I'll find out the quiescent using this full-blown, and I will try to figure out the incremental performance of the circuit doing this differential and all. So what do you think you will get? So now I am sitting here. What will the linear term be in the Taylor series expansion? It will be 0, right? It's a maximum, right? It will be 0. So the entire genesis of this incremental network is based on the fact that you can neglect the higher order terms with respect to the linear term. So if the linear term itself is 0, you cannot really neglect the higher order terms. So what will essentially happen in this case is that if the linear term is 0, then I mean, you don't even have to think twice. If I say this, if you are sitting there and your input is VA plus VP sine omega t, can you comment on the component? Can you comment on the strength of the component at Vn, which is of the form of, let's say, at Vn you are supposed to get some DC, right? Vn DC plus some term times delta V times some f dash plus some terms times delta V squared, right? So, or I should say f dash delta V. And so on. So clearly in this case, this is 0, right? So you will not have anything which is VP sine omega which is of the form of sine omega t. You will have this delta V's. I mean, obviously in this case, the delta V has to be translated back to the input, but essentially what I'm trying to get at here is that, so the terms that we'll get will be proportional to VP squared sine squared omega t, right? You will not get any term which is proportional to VP sine omega t. And that is because your f dash is 0 around this point. Since your f dash is 0 at this point, you cannot do this incremental analysis anymore. If you are faced with a nonlinearity and the operating point is around the maximum or the minimum, right? Again, the outcome of Taylor series. Yes.
Proportional to sine omega t statement that you don't.
Okay. So do you buy this statement that if everything is linear, right? Only f dash exists, nothing else exists. Then I will, at Vn, I will get a DC term plus some term which is proportional to VP sine omega t. Do you agree? So what the point that I was trying to make is that since f dash is 0, you will not get a term which is proportional to VP sine omega t. Does it make sense? So now if you say that I have a cubic nonlinearity, then maybe when you expand a plus b whole cube or a plus b sine omega t whole cube, you can get some remnant of sine omega t that is coming out from that cubic nonlinearity, right? So you have like 3a square b will give you 1 sine omega t. But I mean, forget about this. Those are for different courses. I'll not burden you with those concepts in this. But what I'm trying to this reason, I mean, the opportunity presented itself from a mistake that I made. So I just wanted to make the point that if you are ever in your later on in other circuit courses, or even let's say you are experimenting with novel devices where you end up with these type of characteristics and you want to try to figure out how your circuit performance will get affected by IV characteristics of some new devices that you have been experimenting with, then you have two ways to go about it. One is you can say that I will use incremental model, but you can use incremental analysis. And as I said, you can always reduce your input to smaller and smaller values so that your incremental value analysis still holds. Incremental or Taylor series expansion still holds, where you only have the DC and the first order term. But if your differential itself is 0, it doesn't matter how small you reduce your input to. Then you cannot neglect the higher order terms. Then after the delta V, after that F dash, you have to move on to the next one, which is maybe F double dash. And then you have to do your analysis using that, right? So again, not a part of this course. There will be no questions which will be set on this. But if you're interested, this is something that you should keep in mind. Okay, so does that answer your question, or you have another one? Okay.
Sir, in this question, we need increment. We need to solve for increment.
Right.
So can we say that increment plus total part will be in the negative slope region? Can't we solve?
Okay, so the issue that you will find is the problem. Yeah, so what you are essentially saying is that the increment of plus total part is here, but what happens, it can as well happen that if you are incrementing, the output is reducing. Negative slope essentially means that, right? So which essentially means that when you are moving here, moving to the left. So you will find a case where essentially the solution doesn't exist. You go to the left, the left is trying to push you to the right, and that is trying to push you to the left, right? So essentially that's what is going to happen. So that's why, I mean, firstly, generally when you face these type of problems, then you assume that, I mean, not only in circuit, right? In any domain, you have essentially a region of convergence issue, right? So maybe this type of curve exists, I will assume, for all Vn in this case, and the other curve exists for all Vn, I will assume. Then I will try to Venn diagram, right? Find the set of conditions for which the conditions of the devices are satisfied. If you find a solution with that, that is a solution that you will actually get. But if no solution exists, then obviously this is not the only outcome of that is that this device is not realizable. Because if you put a device, you are supposed, I mean, you can always observe a voltage and current, right? So if you cannot observe if the mathematics is telling you that these observations are null and void, which means naturally these IV characteristics is null and void, which means such a device cannot exist, right?
But for the question solving, there was increment in this voltage.
Yeah.
So
the question was wrong. That's what I'm telling you.
So what about the marks?
Yeah, we'll make sure that you are not penalized for my mistake, right? So don't worry about it. Right? Okay, fine. So, so in the last class, some of you told me that maybe half the batch has taken years, so half the batch hasn't. So I wanted to take this class and maybe part of the next class to quickly run you through some of the network theorems, which are essentially backbone of any circuit design course. Right? So, I mean, some of these might be very obvious for you. Some of these you already might know. So bear with me. This is just to essentially tie everything together. Okay, so let's start from the very basic. So KCL, right? So what is the genesis of KCL? Charge conservation, right? So if I take any volume and I say that I have bunch of ways I can push in charges into this volume, then if I say that there is no charge buildup inside that volume, then I1, I2, I3, I4, I5. So summation of IK equal to 0 if there is no charge buildup inside V, right? So this is V. So that essentially is, in a nutshell, that's what KCL is. So if you have a network, with whatever, you can make any network, doesn't matter. And you are not you are not inside the devices. So these boxes are devices, you are not inside the devices, but outside the devices, you pick up any volume, any closed volume. So what this is telling you is that the summation of the current that is going in and is essentially equal to 0, which essentially means summation of the current going in is equal to summation of the current coming out. That is KCL. What is KVL? What is the genesis of KVL? Energy conservation. Okay, energy conservation is particularly not the genesis of KCL, because if you use energy conservation, there is one assumption that comes into picture. Yeah, okay. I agree, but there is even fundamental something that is related to it. Have you heard of Maxwell's equations? Okay, so one of the Maxwell's equation is, among the four, one of the Maxwell's equation is curl of E is equal to minus del B del T. Okay, so I'm sure you have you know what curl is, right? Engineering maths. So whenever you see curl, you know there is a loop, right? So curl is essentially the integration around a loop when the area of the loop is tending to 0, right? So if you have delta S, so essentially what I'm saying is that you have a loop. And in the loop, it doesn't really matter what you have. If you have a resistance or a capacitance or even a piece of wood, it really doesn't matter, right? Maxwell equation is valid. So you can have whatever here, it really doesn't matter. These can be batteries, this can be a piece of wood, this can be a potato, I don't care. Anything, it can be anything. So what is this equation telling you? This equation is telling you is that if this is the surface, if this area of this surface is S, and if delta S, or rather if I say this area of the surface is delta S, when this delta S tends to 0, you get the integral of the electric field, if you go around the loop, divided by delta S, where delta S tends to 0, is equal to the rate of change of the magnetic flux that is coming out of it, right? So if there is a magnetic field, this is coming out of it, then this, whatever is the equation on the left, is equal to the rate of change of the magnetic field, right? Again, Maxwell's equations, Maxwell's law. So now if yes. Delta is just area of the surface, where delta is tends to 0. So the integral form of that is essentially what I have rewritten. So
would we have to integrate also on the right hand?
No, you have to if I remove that limit. And so essentially, so this will happen, right? So if the integral form will be, you come here and do this. Okay. So you know what is B dot ds, right? Flux, right? So this becomes minus delta phi delta t. And so what this is essentially telling you is if you what this is telling you is that if I divide this loop into small pieces, incremental small pieces, sorry. What this is telling you is that if I divide this loop into small dls, and I observe the electric field within this small dl, and I do E dot dl and go around the loop. Essentially, what I'm telling you, what I'm getting at is that if I observe the potential difference across, in these small dls, and I go along the loop, so I will essentially get now. So this is now. Let me say this is VAB. This is AB. This is VAB. This is VBC, and so on, right? So if I keep going like that. So summation of all voltages in the loop is equal to rate of change of flux. So KVL holds when this rate of change of flux goes to 0, right? So only when minus del phi del t in the loop is equal to 0, then KVL holds. Now note that, I mean, some of you might already be thinking, hey, this seems like EMF, right? So we have inductors. Inductors are based on the fact that there is a rate of change of flux. Why am I saying that KVL holds? Because it seems like inductors also, if you have inductor, KVL also holds. So the statement that I am making is that I have not considered if delta phi delta t is non-zero inside an element. Okay, so if the delta phi delta t is non-zero inside an element, you have to handle that. You have to handle that at the element level. But this statement of delta phi delta t is 0 is essentially what I'm trying to get at here is that if you observe the whole loop and if you observe the flux coming out of the loop, right? So there is no rate of change of flux that is coming out of the loop. There can be rate of change of flux inside an element. Okay, so there you treat it differently. There you cannot really say E dot dl equal to 0, because then in that case you will not be able to get the properties of an inductor. So any design, any engineering discipline, essentially building layers of abstraction to make life easy. You cannot really solve Maxwell's equation to build circuits, right? So, I mean, in principle you can, but when you have to design when you have to design complicated circuits or bigger and bigger circuits, you cannot be sitting and solving Maxwell's equation. So what very smart people before me have figured out is that if you put layers of abstraction and you say that in an overall circuit, I will ensure that the flux, if I observe any, if I build a circuit here and if I put a battery here or maybe a resistor here or inductor there and a capacitor there might be rate of changes of charge buildup happening inside a capacitor. There might be flux changing inside the inductor, but over this vacuum, nothing is happening. So that is why if I go around this loop, which has all those stuff, my KVL will still hold in the form that we need. Okay. Okay, fine. Many of you must have, I mean, I'm sure we'll be knowing this, but this is something that you have to keep in mind because it's always good to know that from where these things have come, which we are using in our day-to-day life. Yes. Somewhere I have you. Not necessarily, right? So this is, I mean, it need not be. B can be, B need not be constant. So if B is constant, B comes out, right? Oh, yeah. Correct. Yeah, I messed that up. There has to be an integral. Otherwise, it's not a, yeah, right. Thank you. There has to be integral. Otherwise, it's not even a phi, right? Yeah. Thank you. Yes.
So in case of transient circuit, the I will change.
Right.
So B will change.
Yeah.
So flux will not remain constant.
Right.
We do transient analysis.
Right. Right. So I changes, B changes, flux doesn't remain constant where? So the assumption is, again, so in reality, it's not true. This is again an approximation, right? So his question is when, if I have a circuit here, just simple current, voltage source and R. Clearly, the current through this is changing. Current through this loop is changing with time, right? So flux is not constant, right? So which essentially means that if you take one of those magnetic compasses and you keep the compass here, you will see it, then it will move. But if you come away from it, then the needle will stop moving, right? So that's the assumption. So you are far away, right? So there are circuits, I mean, when you, some of you might be taking some advanced courses later on some advanced courses on transmission lines, antenna, those like essentially 340, I think, right? So there you will see that these assumptions are not necessarily true. So one comment that I made is that you have to be far away from where things are changing, which essentially means that there is a distance associated with it for these things to be valid, right? So there are certain approximations. Again, when we say these we are replacing something with an R, we are replacing something with an L, we are replacing something with a C. These are again set of approximations. Nothing is a full R, nothing is a full L, nothing is a full C. Everything is a part of these in some mode, right? So essentially what I'm getting at here is that the model that all these lump things are valid because you have done some approximation, and you have done some approximations even when you have been doing F equal to MA, because you are not particularly bothered how the object looks like. You are doing a point mass approximation, right? This is similar. This is a lumped element approximation, right? So I am not particularly bothered how the resistor has been made. How long is it? Or how an inductor is made? How long is it? What shape it is? I am replacing that entire thing with the abstract value. That value, I mean, I'm drawing a resistor like this, wiggly something, but in reality, a resistor doesn't look like that, right? A resistor has some shape, and it not particularly be a single type of shape. It can be anything. So what I am, so essentially, it is some sort of approximation, and the approximation is based on the fact that if there is some change of charge, some change of flux anywhere in those individual elements, they are confined to the boundaries of the element. In reality, it's not true again, because the flux has to come back. But what I'm saying is that my loop is broad enough, long enough, so that, or wide enough, so that for majority of the loop, it's not valid. I mean, sorry, the approximation is still valid. If it's not valid, then you cannot use these set of laws. You'll have to go back and rewrite your equations. You have to reform them. And that is essentially, I mean, some of these, the effect of dimensions come into picture when the devices either become very large, right? So essentially what I'm saying is that this R doesn't take into account how big the arm is, right? The physical dimension of this hasn't come into picture. So when the physical dimensions of it comes into picture, then you have to rewrite your equations and you have to do your analysis again. And something similar happens when you do transmission lines. I mean, you have these high voltage lines that traverses thousands of kilometers, right? From one end of the world to the other. So again, which essentially means that this is probably not true. So you have to use transmission lines for, I mean, equations or the concept that you will see, which takes into account the physical dimensions of the device. Now, again, when I'm talking about physical dimensions of the device, big or small, it is obviously with respect to something. Nothing is big or small in absolute, it's with respect to something. So as it turns out, that is essentially the wavelength of the frequency of interest, right? So again, I'll not go there, but so that's why you see, right? I say circuit design is a fascinating field. It puts together multiple concepts from multiple domains, and you have to build a system. Whenever you're building something, it becomes interesting. Okay, fine. So we're done with KCL, KVL. I had talked about one theorem few classes back called substitution theorem. I had a feeling that you were not satisfied. So let me formalize it. So what is substitution theorem? A substitution theorem is essentially the fact that if you have a, let's say you have a network, I mean, this can be interconnected also, doesn't really matter. And I say that I have observed the voltage at this is point A, this is point B. So I've observed the voltage difference between these two nets to be equal to VAB. And I've observed that the current through this is IAB. So substitution theorem is telling me is I can replace this entire, this VAB, IAB, I mean, this stuff with either a voltage source of value VAB, or I can replace this entire stuff. I'm just only redrawing this. With the current source of value IAB. And nothing will change in the rest of the network, which means what substitution theorem is claiming is that in the circuit on the top right, the current here will still be IAB, and on the circuit on the bottom right, the voltage here will still be VAB. So this is the claim on the substitution theorem. Okay. So it can be intuitive, but I mean, we can also prove this with, I mean, again, somebody said this is a jugaad. Yeah, with some, I would say, regard. Right? So what I am getting here is, let's say, I mean, let me try and prove this one for you first.
So you are assuming any kind of non-linear.
Yes, good point. So see, I mean, the substitution theorem is not limited to, it has to be linear, it has to be time dependent, time independent, LTI, nothing, right? Any network. This statement doesn't take into account the fact that there is no constant on linearity. And that's what makes substitution theorem very powerful. You can use it everywhere. Okay. Not necessarily. Why do you need to set it to be steady state? This can be IA, this can be VAB of T, this can be IAB of T. It need not be steady state. As long as you can replace, as long as this, whatever source you have replaced it mimics this, as long as you have replaced, whatever source you have replaced it mimics this VAB across time. It doesn't really matter, right? Okay. So let me take this example. So you had a current of IAB through this network, and you had a voltage of VA here, and you have a voltage of VB there. This is what we started off with. And let's say that you had, again, if I add zero current to a net, nothing changes, right? So I'll add zero current. So, and I can add zero current in multiple ways. So one way I will do is I'll say I will push current IAB and pull current IAB out. And let me remove this. This is coming in. There is a network. You have to, I mean, be cognizant of the fact that there is a network around it. Similarly, what I'll do the same stuff here. I'll pull current IAB out, and I'll push current IAB in. And again, there is this network here. Okay, no harm done. So note that what is the current through this piece of short? It has to be zero, right? So if it's this, similarly, the current through this piece of short is also zero, right? So if I remove a zero current short, a zero current element, nothing changes in the circuit, right? So I remove this. So this voltage is still VA. This voltage is still VB, correct? So I can now say I'll get rid of this entire stuff. This is not a part of my circuit anymore, not a part of the requirement anymore. And I will connect these two, right? I can do whatever I like with the other terminal of the current source because it doesn't really affect the terminal that is attached to the circuit. Now so can you comment whether, what is the next step? Two current sources driving the same current. I can replace with one. So what I'll simply do, I'll just replace this with the current source of value IAB. And note that throughout this argument, the voltages that VA and VB have remained identical. Okay. So essentially, this is the statement of, or rather proof of substitution theorem using current sources. Okay. Again, very powerful theorem because it can be used across time. For all times, and it doesn't matter whether your stuff inside is a linear circuit, linear network, nonlinear network, whether there's a source inside, don't have a source inside, doesn't really matter. You can use it across. Okay. So similarly, you can do the same thing for voltages. Yes. Okay. So good point. So what he's essentially saying is that, have I skipped a theorem somewhere? So I have IA, I have IA. What I essentially did was, okay, so let me write it in this way. So let's say I have a net, I have current IA coming in, current IA going out. Okay. So if I observe this between these two terminals, let's say A and B, and I put this in a box. Okay. So, and I am not interested what is happening inside the box. I'm only interested what is happening at the terminals. Okay. So from A, what am I observing? A current IA is going in, and from B, a current IA is coming out. So essentially, I can say that for the purpose of this observation, the stuff inside the box, we'll replace it with this single current source IA. Then the observation is still valid because at the terminal, I am still saying at the node A, a current IA is being sucked in, and at the node B, a current IA is getting sucked. Make sense? It is not a substitution theorem, right? This is not really telling you. Okay, why do you say this is a substitution theorem? No. So that argument of what is don't care inside the box comes in many number of theorems. But substitution theorem is essentially saying is the theorem of substitution is I can replace any element. That element can be a resistor, a capacitor, or a transistor, or anything. As long as I replace the two terminals that I'm observing with a voltage source and a current source, or a current source of corresponding voltage or current, then the other quantity doesn't change. If I'm replacing it with a voltage source, the current doesn't change. If I replace it with the current source, the voltage doesn't change. But here I didn't apply that. Here, what I assumed is that if I have two current sources in series, I can replace them with one current source. Right? So that's the critical difference. This is, I think it's called source transformation, source transportation. Something I might I have to recall. I don't want to commit without recalling, but yeah. So something similar is there in terms of voltages also, right? For example, let's say I have a node here, and I have a voltage source here. I have a node here. Let's say this is terminal VA. This is node A. This is B. This is C. I can push this voltage source through the nodes, and I can essentially say that this is equivalent to, if this is, let's say, I don't know, V alpha, let's say. So these two cases are identical. This is basically, the other one was putting two current sources in series, and this is essentially pushing a voltage source to a net. Again, obvious things, but sometimes for folks who will take ESO or folks who have taken ESO, you'll see that this star delta conversion and all those things come into picture. These things become handy, I mean, in quick analysis of a circuit, right? So as long as you know KVL, KCL, everything will hold. But I mean, sometimes you want to do it quickly. So these are some of the theorems that is similar to geometry, right? If you know the initial theorem, you know everything, but sometimes knowing other theorems help. Okay, fine. So substitution theorem with voltage sources. So again, so you have the same stuff. This is voltage VA, this is voltage VB. So what I'll do is I will connect a battery of value VAB. Right? Another side is open. Okay. So what will be the voltage at this point? It will be VA. Okay. So now you see where am I going. So now if I have, now what happens if I connect this? Okay, so let me do this in a different way. I am observed. So what I am essentially trying to get at here is the current that is coming out is IAB, current that is going in is IAB. So if there are two voltages in a network which have identical, two nodes in a network which have identical voltages, and if I connect them together, nothing really changes. Do you agree? The rest of the network, nothing really changes, right? So again, so this is a black box analogy. So if I connect these two, the stuff outside the black box will not experience that anything has changed, right? Because I have essentially shorted two nodes with identical voltages, right? Nothing should change. But inside the black box, something will happen. What will happen? Now the current that is flowing in IA, we will choose to go through this because it's a voltage source, right? Because it can choose to go through this, I can essentially remove this.
Sir,
yes.
Is it a matter of concern that what path would the current take, whether it would be the VAB that is dual or
Okay. Good question. So what he's essentially saying is that how do I know that the current will choose to go into the battery and not that element, right? Okay. So now tell me what happens if I have something like this. Okay. So as far as and I say that let's say this is VAB. Okay. So if I change, let's say any part of this R1, R2, R3. If I change the any element R1, R2, or anything else that is connected to it, yes, will the voltage across RS change?
no?
If the voltage across RS doesn't change, will the current through RS change? No, right? So then if that doesn't change, will now if I say that if I change these values of RS, right? If I change the RS from 1 ohm to 1000 ohm, I don't care, whatever. I mean, there can be a change in RS, and rest of the circuit hasn't changed. Okay. So then will the current through the rest of the circuit change?
No.
No, right? Because for the rest of the circuit, this is equivalent to this RS might exist, might not exist. That's the problem of the voltage source, that it has to supply current to RS. But it's not a problem of the rest of the circuit, because for the rest of the circuit, it's still getting the full voltage, right? This terminal is still VAB, right? So it really doesn't. So if you have a voltage, if you have an element directly shunted with a voltage source, you can essentially remove that element for the purpose of the rest of the network. So the voltage source has to supply that extra current to that circuit, to that element. That's the problem of the voltage source of the person who has designed the voltage source. But for the rest of the circuit, it really doesn't matter. Okay. Yes.
So if we connect two ideal voltage sources, equal ideal voltage sources in parallel, then the current passing through them will be equal, or it can be negative.
Okay. Okay. So that's one of those questions, right? We keep on asking. I mean, even I used to ask this question when I was in 11th, 12th. So let's say this is 1 volt. This is 1 volt, right? So if I now note that, and if I have a network here, right? So your question is, if I had a 1 volt battery, I probably had, let's say, whatever, IA current. Now, if I have another 1 volt battery, I'll still have IA current. So how does this current divide between these two batteries, right? The correct answer is that we don't know. It depends on the internal resistance of the battery then. So you'll have an internal resistance. Now, then you have to see how the internal resistances of the battery are, because you are essentially, yeah, so then you don't know, right? Then, I mean, then I can as well say they divide equally, but we don't know. Essentially, that's the crux of the answer. Yes. But if somebody says that it's not, you cannot even argue, right? So on account of symmetry, yes, but symmetry comes from some other issue. We will not go there. But essentially, if I say that I have RS, then you say that the rate of change and the way RS is tending to 0, right, is same. Then yeah, in the limit, both of the currents are same, right? But if you start off with assuming that they're exactly equal to 0, then battery is essentially an ocean, right? It's an ocean of charge, right? So it can supply, I mean, whichever wants to supply, it can supply. But mathematically, you cannot really pinpoint whether it's coming from this or that if you don't take internal resistance into account. Okay. Because essentially, if you put two oceans together, I mean, two infinities together, you get another infinity. That's essentially the problem, right? Okay, fine. We are almost out of time. I presume you know this. Do you know Thevenin's theorem, Norton's theorem?
Yes.
Okay. Do you know the derivation of that? Yes. Okay, fine. So we'll start off the next class, which will be on Friday. We'll run through some of the obvious ones. Pardon? I haven't yet decided, but you won't be penalized for my fault. That can be rest assured.